Hello everyone, my name is Frédéric de Gauzet, I'm from Grenoble, and I wish to present you some work that is a collaboration with my colleague Baptiste from Düsseldorf, which originates from the fact that I've been using SACS and collaborating with Baptiste on Atom Probe for quite a while now, and we tried recently to answer the following question: can we use this interaction between SACS and Atom Probe to actually evaluate the effective spatial resolution of Atom Probe and its impact on precipitation or clustering studies in a context which is not an ideal context, which is where the actual ideal spatial resolution of Atom Probe is usually measured in pure alloys or in pure elements close to crystallographic poles, etc. So this is not the case here. So the way we're going to do this is to use SACS, and this is the typical slide I show at the beginning of a SACS presentation, but here I will not detail it. But what's very important to notice is that SACS is a diffraction experiment. It's a reciprocal space technique, and the SACS intensity is actually the exact equivalent. It's a Fourier transform, so it's the same thing as a correlation function in the direct space. Okay, so direct space, correlation function, reciprocal space, SACS intensity. Now, the correlation function is something that the Atom Probe community called RDF, or radial distribution function. It's more or less the same thing. It's just another way of expressing it. Okay, so the idea here is that since we are looking at the same thing, we can use the same formalism to interpret both type of data, and we have actually shown this already in a collaboration with Huan Zhao, who did her PhD in Düsseldorf as well, and we did a couple of papers that you can check out if you're interested in. It happens that she, you can listen to her talk in the plenary session because she had an early career researcher award, so congratulations to her. And here I will use this data as an example, but the idea is that on an aluminum zinc mag, we use the same interpretation formalism to interpret SACS and Atom Probe data. And the result is that we can compare directly the size of SACS and the size of Atom Probe, and the agreement is actually very nice. So you can see SACS is in situ, so you have all the points, and Atom Probe is obviously ex situ, and see that the agreement for size is very nice everywhere, except maybe for the very larger size, where the statistics is a bit less good. Of course, there are fewer precipitates, and also because these precipitates are very dense because of local magnification, so they may actually appear a bit smaller than they are. So it sort of makes sense that we don't get the right size. Now, this actually led us to think that we may have a good way to assess the spatial resolution of Atom Probe, because SACS essentially has no geometric uncertainty. That's a very interesting point, because it will enable us to have a standard, to have a reference, because this is one of the reasons why we never had the chance to actually measure in real useful cases the spatial resolution of Atom Probe. That's because we never had a good reference. But actually SACS can do this. What we have done really is to really think of an effective spatial resolution. We know there are plenty of different effects there, but the idea here is we are here in a user perspective, and we want to measure clusters, we want to measure precipitates, we want to assess the effective resolution that makes, if I measure an atom at this position, what is the probability that it actually was at this position before. Now, if I want to compare size from atom probe and size from SACS, I can plot it on this kind of graph, size from APT versus size from SACS. And you see that for these aluminum zinc mag alloys that we've shown previously, they all line up very nicely on the diagonal, except for the larger one. We have already discussed this. So it means that we have a very good agreement. So that's nice. And now the idea is, okay, maybe I can add the other data that I have where I actually happen to have measured both atom probe and SACS on the same sample, so that I can actually add them on this graph. And this is what I've done. These are aluminium lithium mag alloys, which precipitates L12 spherical precipitates. I've shown them in Trondheim, at ICAA in Trondheim a few years ago already. And you see that they actually line up very well as well. Then I've added chromium decomposition in stainless steels, in pink there, clusters in aluminum, lithium, copper, etc. And you see that while for the big ones, you're all lined up very nicely on the diagonal, for the small ones, it's a bit different. It seems that there's some sort of saturation of the size to a value of about 1 nanometer. Now, if you think about what would an effect of an effective spatial resolution that would be Gaussian, a blurring of the atoms, on this kind of graph, well, I've calculated this with this. It's the solid line there. If I blur the position of the atoms with a Gaussian noise of sigma equals 0.5 nanometers, then the apparent size that I will measure will follow the diagonal for large size, and then will saturate to a minimal measured size, which will be twice the sigma, 2 sigma. So in this case, about 1 nanometer. So you see that if you calculate this for 0.5 nanometers and also for other values, 0.2 or 1.2, you see that all my points, they're all nicely in this shaded area, meaning that actually our data show that this is compatible with a 0.5 resolution, 0.5 nanometer resolution, with of course large variations. So that's the first way of measuring this. I've added other data points from the literature in the actual paper, so if you want to check it out later, you can. Now, there is another way to estimate the spatial resolution with this kind of measurements, and which would be to think of it like a point spread function. So it's really, I image the smaller objects I can think of, and in its effective, its apparent size will give me the actual resolution. So the smaller objects I can think of are clusters in 6000 series alloys. So I don't know exactly what size they are, and unfortunately you can't measure them in SACS, but we know they're probably very, very small. And interestingly, for 12 different data sets, we've all measured them at around 1 nanometer. So it's actually also very compatible with a 0.5 sigma spatial effective resolution. Now, there is a third way to measure it, to measure the spatial resolution, which is to assume a sharp interface at the precipitate. So for this, you'll have to concentrate on the bigger precipitates. So I went back to the aluminum lithium precipitates that I've measured some time ago. And on these precipitates, you can, which are L12 precipitates in the matrix, you can safely assume that the interface between the matrix and the precipitates is reasonably sharp. And if it's sharp, then if you compute the RDF, the correlation function, then there is what us SACS people call the Porrode law, which actually is for reciprocal space, but is the same in the real space. And this law in real space tells us that the slope at the origin of the correlation function is related to the specific surface, that is, to the radius. And if the slope is 0, it means that you have a diffuse interface. And you see that in our case, well, the slope at 0 at the origin is actually 0, and you can fit this with a resolution of about 0.66 nanometer. So we have again a third estimate of the resolution, which is compatible with a value around 0.5-ish nanometers. Now, what is the effect of a 0.5 nanometer resolution on an atom probe dataset? So here I made some very simple sketch. These are in 2D, but it'll be the same in 3D. I take 100% solute spherical clusters of radius of 0.5 nanometer here and radius of 1 nanometer here, and I just apply a blurring of 0.5 nanometer resolution, and you see what you get. So you see that your clusters completely disappeared, and you see that it was 100% solute, and here of course it's not 100% solute anymore. And of course what you can directly see here is that the local environment of the atoms, their direct neighbors, etc., they completely disappeared. You can't actually retrieve the local environment. It will be a miracle if you could actually tell whether these two atoms were actually nearest neighbor in the original volume. And also, you have to put these 0.5 nanometers in perspective with the typical Dmax, the distance used in cluster search algorithm, which is typically of this order of magnitude. So you already see that in typical clustering context, you will be in trouble if this is actually what is going on. Now, we made some better simulations on simulated volumes with 100% 3D precipitates, spherical precipitates, where we here on the left, what we did is for different sizes of spherical precipitates, we measured the radial concentration profile. So it's really an ideal proxygram that we did here. And you see that, for instance, for the big ones, it's supposed to be a step there. It's 100% and then 0. But in fact, you see that the interface is diffuse, but that's fine. And for smaller ones, as big as 1 nanometer already, you see that the composition at the core is only 70% here, and for the 0.5 nanometers, it's only 20%. So even on a 1D profile, the concentration at the core is no more 100%. It's even worse if you average the concentration of the clusters. That is, if you it's some sort of ideal cluster search analysis. I do a cluster search. It gets me these clusters, and it gives me the average concentration in these clusters. And you see that the average concentration, even for bigger ones, like the 8 nanometers, will already be about 80%. And of course, for the smaller ones, it's not even 10%. And these were 100% solute clusters, so keep this in mind. So this value of 0.5% resolution is actually a good one. It's an excellent resolution, spatial resolution, but its effect on the actual results is probably a bit harsher than most people would expect. So as a conclusion, we can say that since atom probe and SACS speak the same language, and that SACS has no distortion, we can use it to assess atom probe effective spatial resolution. That's very interesting. And we actually find that it is in the order of 0.5 nanometers for sigma. So it means 2 sigma is 1 nanometer. So it's actually a very good value. But it's a bit higher than most people would have put forward. And its effects on the apparent composition and the size of objects needs further investigation, but we've shown already that it's probably a bit more than what's expected. And it probably also questions the way we treat clustering studies in atom probe. It's especially true for the 6000 series studies, where atom probe is the only way to study the clustering, and maybe the impact of the resolution is a bit higher than we think, and that's what I try to sum up in this conclusion. That is that the enemy of clustering in atom probe is resolution. It's not detection efficiency as some people would try to tell you. It's really only resolution, which is really related to the phenomenon of evaporation. So with this, I thank you for your attention. And if you want to have more details of more information, don't hesitate to contact me, and please read this paper of ours that we've published in Actamat about this thing. Thank you very much.